8.5.1 is solving systems of linear equations. So in chapter 4, we talked a lot about linear equations and, how to graph a linear equation. It looks like a line, how to graph using slope-intercept form, how to write the equation of a line, if we have the graph or if we have 2 points, and how to find the slope and all that. So we were working with one line. This chapter is going to be about systems of linear equations. So we'll start with the definition. A system of equations is any two or more equations that have the same variables. So they're typically graphed in the same plane, so on the same coordinate plane. And in this case, since we're talking about linear equations, it'll be two or more linear equations, typically that both have x and y variables, and we graph them in the same plane. So it'll be two lines in the same plane. So here's an example of a system where we have two separate linear equations. The first one is x plus y equals 7, and the second one is 2x minus 3y equals negative 11. And the reason this is a system is because it's two separate equations, and they have the same variables. They both have an x and a y. So we would call this a system of linear equations. Now, the second part of this, and what we're going to be working on in this chapter, is solving a system of linear equations. So the solution to solve is when we find an ordered pair, and remember an ordered pair is always written in parentheses with the x coordinate, comma, y coordinate. Okay, so an ordered pair that will make both of the equations true. So that's the solution. If you're asked to solve, your answer will always be an ordered pair. Oh, that came up 2 times. Rewrite it so it's clear. Okay, the other way to figure out the solution to a system of linear equations is by looking at a graph. So there are multiple ways to figure out the solution. The key is that the solution is always an ordered pair. So whether it's you plug in an ordered pair to see if it's a solution, or you can look at the graph of the linear equation, and the point where the two lines intersect is the solution, because that point is on both of the lines. So it is a solution for both. It is part of both lines, and that intersection point as a ordered pair is the solution to your system. So let's look at an example. The first example, and sort of the first set of questions, will be asking you, is the ordered pair a solution? So it's going to give you an ordered pair, for example, 2, 5. And it's going to be asking us, is this ordered pair 2, 5 a solution to this system? Remember, ordered pairs are x, comma, y. So what we're going to be doing is plugging this ordered pair into both of the linear equations to see if it makes a true statement. So let's start with x plus y equals 7. So if we plug in 2 for x plus 5 for y equals 7, and simplify, we get the statement that 7 equals 7. So far so good. It is a solution to the first equation. In order for it to be a solution for the system, it has to be a solution to both of the equations. So we have to test both. Let's plug in 2 for x. So 2 times 2 minus 3 times 5 for y equals negative 11. And then simplify. So we get 4 minus 15 equals negative 11. Simplify. Negative 11 equals negative 11. So this also turns out to be a true statement. So when we plugged in that ordered pair, 2, 5, into the system, we got true statements for both equations. That means that yes, this ordered pair is a solution to the system because it plugs in and gives us true statements for both. The second example gives us this point 2, 0. Okay, this is our x and our y. And we're going to plug in x and y to both equations to see if it's a solution. So I'm going to plug in 0 for y is equal to negative 2 times 2 minus 4. And then simplify. 0 is equal to negative 4 minus 4. Make sure you're careful with your math. Negative 4 minus 4 gives us a negative 8. So this is not a true statement. 0 does not equal negative 8. So because this ordered pair isn't a solution to the first, actually I'm not going to put an X, to the first equation, this ordered pair is not a solution to the system. The rule is it has to be correct for both in order for it to be a solution to the system. So we would say no, that ordered pair 2, 0 is not a solution to the system. All right, so then the second part of this is solving using a graph. So to solve a system using a graph. In order to solve by graphing, you are going to graph each equation, and you're going to want to get it into slope-intercept to be able to easily graph this by choosing x values and solving for y. Then you find the point of intersection, so where the lines cross, that point where they intersect. And then finally, the point of intersection, whatever that is, it will be an ordered pair. And that point is your solution. So you always write the ordered pair as your solution. That's the solution to a system, is the ordered pair. One thing to note, parallel lines have no solution. So if you ever graph and you see parallel lines, they will never intersect. So there cannot be any solution because there's no intersection point for parallel lines. Okay, let's look at an example. All right, example 2 says solve by graphing. So what we're going to do is graph these lines and then figure out the point of intersection. So I'm going to call this equation 1. And remember, in order to graph, we make our function table. We choose values for x. And so in this case, I'll do my normal -1, 0, 1. And then I plug in -1 for x to figure out what y is. So when I do -1 for x, I do -2 times -1 plus 5, which gives me -2 times -1 is 2 plus 5. Oops, getting ahead of myself. So 7. So 7 is my output, and that is an ordered pair. So I can graph this over here, -1, 7. Plot and label. Okay, then I can plug in 0 for x, -2 times 0 plus 5. So that simplifies to 0 plus 5, meaning my output is 5. So my next point that I can graph is 0, 5 right here. And finally, I can plug in +1 for x, -2 times 1 plus 5 gives me -2 plus 5, which gives me an output of 3 when x is 1. So the last point that I can plot here is 1, 3. Okay, and then I connect the points, making sure that my line goes all the way through, because I don't know where my other line will intersect. So I want to make sure my line is nice and long in case it intersects at somewhere that I didn't choose. Okay, then let's graph line 2. Make my function table. X, Y, choose my points. I can use -1, 0, 1 again here. It's works out fine. Plug in 4 times -1 minus 1. So -4 minus 1 gives me -5. So my first point that I can graph is down here at -1, -5. Then if I plug in 0, I get 4 times 0 minus 1, which is 0 minus 1, so -1. So my second ordered pair is 0, -1. And my third ordered pair, if I plug in a 1 for x, 4 times 1 minus 1 gives me 3, sorry, not 3. 4 times 1 is 4. Minus 1, which gives me an output of 3. So then my ordered pair is way up here at 1, 3, which happens to be the same point that I saw on my other line. So if I connect these with a line, oh gosh, that's not the straightest line, but you get the idea, just a sketch. So we can see here the point of intersection really clearly happens right here where these two lines cross at 1, 3. And that is our solution. If you're asked for the solution, you give the ordered pair where the lines intersect. Okay, let's look at this one. Tells us the same thing, solve by graphing. So what we want to do is get this into slope-intercept form so that we can easily make our function table and then graph. So if we do this one, I'll do the work and then we'll solve and graph. So remember, we want to get into slope-intercept form. So we want y by itself and positive. So subtract 6x from both sides. I'm going to just do this over here and then erase. So we get 3y equals negative 6x plus 12. And then to get y by itself, which is slope-intercept form, y by itself and positive, we will divide every term by 3. So we get y equals negative 2x plus 4. So I'm going to erase all of this, and we'll call this y equals negative 2x plus 4. All right, so here's our equation number 1. Do that in red. And then the second one is pretty easy because to get y by itself, we just have to subtract 4x from both sides. So we end up with y equals negative 4x plus 14. All right, let's do this. So then make our function table. Let's do this for number 1. X, y, let's do negative 1, 0, 1. And then we'll plug in and get our outputs. So if we plug in negative 1, we get positive 2 plus 4, which is 6. So negative 1, 6 here. If we plug in 0, we get a 4, 0, 4. If we plug in 1, we get 2. So here's our first line, okay, and I'm going to connect my points, something like that. And then if I graph the other line with my function table, we have x, we have y, choose 3 x values. I'm going to make my x values a little bit bigger here because of that 14. Let's do 2, 3, and 4, maybe. Let's see how that works. Okay, so plug in 2. 4 times negative 2 is negative 8. 14 minus 8 is 6. So 2, 6. Way up here. Okay, if I plug in 3, I get 3 times negative 4 is negative 12, plus 14 is 2, so 3 comma 2, 3, 2. And then if I plug in 4 times negative 4, negative 16, so we get negative 2. 1, 2, 3, 4, 1, 2. For some reason I feel like I'm doing this wrong. Let's see. And I did do a lot of it in my head, so that could be the problem. Okay, it could also, let me try to connect these points. Okay, so when I connect these, and this is the problem with like not having a really straight line, you can kind of see it. If I continue this red line, then we can more clearly see sort of that intersection point, which happens on here. So it's way down here, and my graph isn't very good, but we can see that the intersection is happening here. It actually should be down here, and this is the problem because my lines are not straight. Let me see if I can redraw these better. Okay, that's erased and kind of redrawn, and it's still not perfect. This is why a ruler is so helpful, because it actually, helps you see clearly, or using graphing software, which we'll talk about too. So we can kind of see it's not perfect, but the intersection happens right down here, which is at 5, -6. So that point, 5, -6, is our ordered pair. That's the solution. So if we were asked for the solution to this by graphing, we would graph and we'd see that intersection down there at 5, -6. Okay, you can also do this by plugging into a graphing calculator, which we'll get to at the last slide. I'll show you where to go online. Online on Desmos, which is where I'm going to show you at the end, you can plug in without being in slope-intercept form. On a graphing calculator, you have to have it in slope-intercept form in order to be able to graph it. But online on the software, you could have just left it as 6x plus 3y equals 12. All right, and finally, for word problems, you will have to write 2 separate systems and then solve. So here's this one. It says roofing contractor buys 15 bundles of shingles and 8 rolls of roofing paper for $640. Here's our first bit of information. Then it says a second contractor buys 8 bundles of shingles and 2 rolls of roofing paper for $296. Find the price of 1 bundle of shingles and 1 roll of paper. So what we're going to do here is we're going to assign a value or a variable to the shingles. We're going to call all of the shingles X, and we will call all of the roofing paper Y. And then we can write 2 equations here that we'll use to solve. So we know that 15 bundles of shingles are 15x plus 8y, so however much it costs per bundle, added together will equal $640. So that's our first equation up here. Let's do that in yellow so that it's clear. That's our first equation, is the first purchase, and then our second equation will be the second purchase that they made. So a second contractor buys 8 bundles of shingles, and we said that shingles were X, and 2 rolls or 2Y of roofing paper for $296. So if we graph this to solve, we can figure out the solution. So if you go to Desmos and plug it into a graphing calculator, you will be able to see the graph of this looks something like this. Okay. And if we do it with the same colors. All right, so sort of to sketch this. The first equation in yellow is sort of going this direction. Okay, and then the second equation is kind of like this. Okay, and then if you hover on Desmos over that point, it'll give you the ordered pair. So here's what the ordered pair says for this particular equation. These 2 lines intersect at 32, 20. So that's not what they ask, though. It doesn't ask where's the intersection point. It says find the price of 1 bundle of shingles and 1 roll of paper. Well, we go back to what our labels were. We said that X represented boxes of shingles. So 1 box of shingles, or X, we looked at our X coordinate, which is 32. So shingles cost $32 per bundle. And then we look at our y coordinate, and we said y is going to represent the roofing paper. So the roofing paper then, since our coordinate is 20, costs $20 per roll. Okay, so the coordinates in a word problem represent something based on how you wrote the equation. So pay close attention to your labels and remember those. Okay, finally, this is your little helper. Since we do not have graphing calculators that we're actively using, and you will not be using them for the test, you can use Desmos tonight for your practice, and it's a great online tool to be able to use in general on homework and stuff like that. Go to desmos.com, and when you get to the website, you're going to click on this button right here that says graphing calculator. That will take you to the calculator where you can input linear equations and find their intersection. So you may have to zoom in or out depending on the equation and move around a little bit to find the point of intersection. But that's how you're going to use, you can use this for your homework tonight to help you solve and practice graphing. All right, that is all.